actual videos, but I didn't show up.
Yeah, yeah. And so apparently that's what a couple of students are doing, or at least one student. He's doing pretty well. We're just watching the videos, but we'll see. Yeah. And so today we're going to talk about the zeroth law of thermodynamics and some basic terminology. Okay. I know. So what happened was they went through and did the first, second, and third laws of thermodynamics, and then they realized temperature never was defined. The fundamental property of thermodynamics, the thermo part of thermodynamics, and they said, well, we can't go changing the numbers, and so you'll see that as a theme throughout science. Once we come up with a numbering scheme, we don't want to throw the literature into chaos by trying to get everybody to change the numbers, right? So first law, we don't want to now make the first law the second law and the second law the third law, because think of how confusing that would be. Even as a student, you're like, okay, that was the first law prior to 2024, and now it's the second law, after 2024. There's no way to keep track of all that mess. So we like the literature to have a common scheme, throughout history. So we have to do strange things like this. This is the zeroth law of thermodynamics. So
They just number things, and they're like, it's not numbered in the order that they happened, just the order that we discovered.
There you go. Yeah. So it's the fourth law of thermodynamics, but it's prior to the first law. Yeah, that's good. So what you've got there is two different. So it's logically prior, but not chronologically prior. Yes. So there's logical priority and chronological priority. So they're trying to do the logical priority here. So the official statement is when two objects are in thermal equilibrium, they must share a common property. Sounds pretty basic, right? And so what do we mean by them being in thermal equilibrium? When they share a common property, and that property is temperature. Then we have the first law. So this is a little different from y'all's notes. I went ahead and stuck them all on one page. Okay, so y'all have the zeroth law, but I'm going to go ahead and list all of them just so you'll see them all. The internal energy of an isolated system is constant, and we're going to have PowerPoints on each of these, so you don't have to worry about like scribbling it down. I'm just kind of giving you the full perspective. And that's where we get the law of conservation of energy and the law of conservation of mass. And after Einstein, we use these as sort of a combined thing. We say mass energy is neither created nor destroyed. We'll do Einstein's famous equation today, equals mc squared. So that's going to be fun. Then the second law of thermodynamics. No cyclic process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. So this is what prevents us from having that perpetual motion machine that we always dream of, that it's like, pulling yourself up by your own bootstraps. And then another way to say this is the entropy of an isolated system increases in the course of spontaneous change. So this idea of entropy being the increase of options, moving towards a more degenerate state of levels or to a denser energy level state. And then the third law of thermodynamics, the entropy of a perfect crystalline atomic substance is 0 at 0 Kelvin. The practical result of this one is that we now have a reference point for entropy, and we can make tables. We can have standard entropy tables, just like we will see that we have standard enthalpy tables and standard Gibbs energy tables. So we'll see the results of those. But here's the thing in your notes. There's the zeroth law, and recall from all that we've done so far, the first 3 weeks of the course, that temperature is the foundation of the Boltzmann distribution, which is the foundation of all of all the other things. So once we have temperature, we can figure out the ratios of the levels, energy levels, their population. And once we have the population of the energy levels, we can calculate the energy, the entropy, the enthalpy, all of these things. So that's a wonderful thing. So temperature seems to be a great measurement for tracking the properties of a system. And in fact, we even do that for our bodies, right? We measure our temperature to see if everything's okay. That one value can give us a diagnostic on a lot of other reactions and things, even in a complicated system like our bodies. So temperature is just amazing. After going through all the statistical thermodynamic stuff, do y'all have any reactions to that? Were you surprised at how much you could calculate by hand? I mean, that's the right answer, right? You know, starting with the temperature of a system and a simple energy level diagram, you could calculate all of these thermodynamic properties, including equilibrium constants. You know, yeah, it's tedious. It's a whole page of math, but it's amazing that you can do that. Yeah. Now, for a real chemical system, we can't do it by hand, and even computers struggle to some extent. But we know the equations. It's just too tedious. It takes too long to calculate. Okay. I'm going to move on so we can keep going. Okay, so let's think about this idea of absolute temperature. How would we know? Like, we've had many different temperature schemes. Can you, which ones can you name? Kelvin, okay. Celsius. The dumb one? What's that one? Fahrenheit, okay. There's also an engineering temperature system called the Rankine. Okay, yeah. And then Celsius is sometimes called centigrade. Okay, so sometimes people see the C and they think centigrade instead of Celsius. It's named in honor of Celsius, who was a scientist in the past. But the centigrade tells you how we came up with it. So we know for water, we know the freezing point of water, we know the boiling point of water, and they just took those two temperatures and divided by 100. So centigrade, there's 100 gradations between the boiling and the freezing point of water. So Celsius is based on water. So that's pretty cool. I don't know what Fahrenheit was based on. I mean, 212, 32, that seems strange. So it's based on something other than water, because no one would pick those numbers just out of the blue and say, yeah, 32 is going to be our freezing point. Yeah, that's right. So I mean, that's something we could probably find on Wikipedia. But let's say we did what?
I had chem teacher in high school said Fahrenheit was based off the human body.
Oh.
Heated it and like, let's do something. They did something else.
Yeah. Okay, that's interesting. Yeah. So if we took these gases, and you see these are different containers. So let's say we had a steel container of these different volumes. So a fixed volume. And I've always wanted to do this experiment. Let's say we have a 0.3 liter container, and at room temperature we have a certain pressure, okay? And then we cool it down, and that's not room temperature, that's 300 Celsius. But anyway, let's warm it up to 300, we get that pressure, we come back down here to 100, we have that pressure, and then we extrapolate that line. So we draw a line through there, and we hit the x-axis here at some negative temperature. Then we put it in a different volume container and redo the experiment. And then we extrapolate that line down to where pressure goes to 0. And we get the same negative temperature number. We pick a smaller container, or ice is a larger container actually, and we redo the experiment, and we come down, extrapolate all the way down. We hit the same temperature, negative 273 Kelvin. And so it made sense to just move 0 down here, right? We've discovered absolute 0. That's the temperature at which the pressures drop to 0. So that would be absolute 0 temperature, the minimum temperature, where an ideal gas volume or pressure would go to 0 with respect to temperature. And so then that moved this up. This is now 273.15 Kelvin. And all of these, you just add 273.15 to all of them, and you have Kelvin instead of Celsius. And so that's why it's so easy to convert from Celsius to Kelvin, because they just slid the scale down, and it's not a multiplication or anything like it is in Fahrenheit. So all these ideal gases have the same x-intercept. They all point to a single temperature where P goes to 0. So this temperature has been defined as absolute 0. Okay. Do y'all have blanks on this page? Or you just write? You do, okay. Okay. So that would be a fun experiment to do. I think that'd be a great experiment for a freshman lab. You know, you could do it very easily with a balloon. So instead of looking at pressure going to zero, you could do volume goes to zero. You could have room temperature water and put the balloon in the room temperature water, and you could mark the level and take it out and then fill it back to the mark, and you can see how much volume it took up. And then you could also put it in ice water. So there's your temperature bath for the cold temperature. See how much volume it took up, and then extrapolate those volumes down to absolute zero and see if you could calculate absolute 0 Kelvin. You know, so I think that would be a fun experiment. I'm not in charge of the freshman lab, so. What's that?
It reminded me of Dr. Bob. Like, yeah, I got like a demonstration for you guys.
Oh wow.
It's when he took like a HEV bag and filled it up with nitrogen and then just threw it at the board.
Oh
He
my
didn't tell
gosh.
us what he was gonna do. He just
Yeah.
filled it up and he threw it at the board. All spurs.
So excited.
It's pretty cool, yeah.
I was not as excited. I was holding the bag. I
Oh,
was
yeah.
terrified.
Yeah. I used to the finale of our little Boy Scout merit badge, chemistry merit badge, would be to blow up a Coke bottle or water bottle with liquid nitrogen out in front. I always tell the campus police, we're going to have a big boom on campus. Don't think it's a bomb. I mean, it is kind of a bomb, but it's not like a terrorist bomb. so yeah, we're over here. You put liquid nitrogen in the water bottle and you cap it, and it immediately starts cracking, pop, pop, pop. You know, like it's going to blow up in your hand. But it takes a while. But if you put it in water, that water is like a heating bath. You know, it's room temperature water. So you drop it in and bam, it takes a few seconds. Well, we put it in there, and I didn't get enough liquid nitrogen in the bottle. And so it goes, and it was like, and it stopped. And it was not going to blow up. And then the boys started running over there to it. I was like, back away.
I said, oh, boy.
Yeah, that's right. So they ran off, and I said, y'all go back to your buses and everything. So they left for the day. And now we had to deal with this really tight bottle, you know. So we knocked it off, and it hit the ground, and it was so tight it sounded like glass. The plastic bottle was like tink, 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 tink. I'm like, whoa, that's tight. So like a little jouster, I got the meter stick, and I was like poking it over into the grass, and we got it all the way over by the dumpster. And then one of our TAs was a smoker, and so I said, light up. And he said, okay. So he lit up, and we taped his cigarette to the meter stick, and I stuck it on the plastic, and then it goes, and that was it. I was hoping it would explode, but it didn't. But he was like, you want me to do what? I was like, you smoke, light one up. So he did.
So this is a trap.
That's right. Exactly. I know. Yeah, that's right. So I put him in jeopardy. Okay, so there's a brief tour of temperature. Okay, let's look at this. There are no negative temperatures, right? So we can get down to really small temperature. 10 to the minus 4 Kelvin is still positive. It's just really small. Okay, we can't reach absolute zero. I'm just making a blanket statement there. Why can't we reach absolute zero? What's that?
Because they can't go negative. So they would the absolute zero. You have to assume that it's like a middle point or something. But
Yeah, I see what you're saying. You're on the right track. Yeah.
there's no opposite end, so it can't be.
Yeah. What would we put it in contact with?
Yeah.
Right.
It would just not function at a certain temperature.
Well, how do we get things to a temperature? We put them in thermal equilibrium with something, right? And they share that property. So you have to have something at absolute zero to get something else at absolute zero. And so we don't really have anything like that. Yeah. It's even like the farthest reaches of space is, like micro Kelvin. So we can get to nano-Kelvin with Bose-Einstein condensation. So we'll learn about that this morning. We can reach mega Kelvin, so millions of Kelvin with nuclear detonations, and those are illegal now, at least, with international treaties. But we can get close with these national lab facilities. Laser confinement is one, and magnetic field collapse, the Sandia Z machine. But you can see up here the Z machine and the National Ignition Facility, they're pretty close to the corona of the sun. So you have the core of the sun where fusion is taking place, and then all of the gases that are blasting out, that's the corona. So that's that luminous outside edge of the sun, and these machines are getting close to the solar corona. And just inside, so a little hotter than the solar corona, that's where fusion is. You're hot enough to create fusion. So that's pretty cool. We'll learn a lot about that in a second. Okay, so let's go to the low temperature end of things, the Bose-Einstein condensate. Now these bosons have even mass numbers, so that's where this word, the scientist Bose, these particles are named after him. Like deuterium, helium-4, neutrons, and so on. They have integer spin. They're not limited by the Pauli exclusion principle, meaning they can all be in the same quantum state. So that's really handy. Okay. And if you look at the speed of gases here, you know, this is from the Pearson book, the freshman chemistry text. So this is the distribution of velocities at given temperatures, right? So at 0 Celsius, this is the distribution of the gas velocities. At 100, you see that there are more with higher velocities, but there are still a lot of molecules that have really low temperatures, really low speeds, really low temperatures. And so one way to cool something is to let the fast molecules evaporate. So if all of these fast molecules evaporate, you're left with these cold ones. And this is what happens. I mean, this is why you're even the coffee in an insulated mug, where there's no heat coming in or no heat leaving through the sides of the mug. The hot molecules leaving the top are going to leave behind the cold molecules. So your coffee's not really cooling down. I mean, it is. There's a lower temperature after time, but it's because the hot molecules have left. So if you want to keep something hot, seal it up. Don't let the radiative heat out. Don't let the collisions with the outside world, convective heat out, and then seal it up to keep those hot molecules in. So this, I'll let you guys follow this link if it's active online. You can click on that and learn about the Bose-Einstein condensates. It's really pretty cool. They have lasers that trap these atoms in space. And back up. The lasers produce sort of that's what's represented by this bowl, this little energy barrier. If you've got a hot molecule, the lasers aren't really strong at confining the atoms. They can only confine the cold atoms. So if there's an atom that's hot enough, it can escape out of that bowl. And so we're cooling it in a vacuum using laser confinement. And so it's not that the lasers are cooling it down, they're just providing a little inertial barrier. So if an atom's trying to go towards a laser, it'll absorb the laser light, and then it'll emit that light, and it'll kind of put a brake on the velocity of that atom. If the atom has enough energy, it'll just overcome the laser and escape. And it has high energy, so it's leaving behind the cold atoms. So that's how they condense these. The goal is to see if they can get translational quantum effects. Remember, for the partition function, we solved for that. What temperature would argon be when it displayed like 2 energy levels, and it was 10 to the minus 9 or maybe 10 to the minus 10 Kelvin for argon. So that's what they're trying to do, to see translational quantum effects. Then we get into the high energy side of things. So this is a fusion energy. And I always was confused growing up. I had learned about nuclear power and nuclear weapons and everything nuclear, and I was very curious about that. But I was confused. How is it that fission, splitting the atom, gives you energy, and fusing, combining atoms, gives you energy? That doesn't make any sense to me, because I thought it must have been linear. Like, if you split heavy atoms and make lighter atoms, you get energy. Well, why is it that you combine light atoms to make heavier atoms, you get energy? And it's because there's this curve of nuclear stability. So it's a pretty flat curve. It's not steep here. Notice I'm missing a whole lot of elements, but iron and all of those elements in the middle, you know, like chromium, manganese, and iron, cobalt, all of those are about the same stability. But iron is a very common, very stable nucleus. And so that's why we can even look at the amount of iron content in a star and kind of see how old it is. Because iron is a sink, right? It gets to iron and doesn't want to go anywhere else. So the heavy atoms would split apart if they're, you know, hit a certain way. They'll split apart and approach iron. And the light atoms will fuse and approach iron. So the amount of iron content that builds up in a star is an indicator of its age. So that's pretty cool. But notice up here, going from uranium-235 down to lead-207. And at the last part of the course, we'll learn how uranium over here turns into lead through alpha particle emission and beta capture, or beta emission and electron capture and all these different things. So that transuranic series that ends up in lead, that's nuclear fission. And we get a lot of heat out of that. And we can turn that heat into steam, spin a turbine, spin a generator, make electricity. So that's how a nuclear power plant works today, using fission power. So look how small that little fission power is compared to fusion. Going from hydrogen to helium gives, I don't know, almost 10 times more power. We have a lot more hydrogen or deuterium, heavy hydrogen. It naturally occurs in seawater. We can separate it pretty easily. We can use that to use fusion power. So let's look at some of the numbers. Okay, so there's a tremendous amount of energy stored in the nucleus. The masses of the fission products does not equal the masses of the reactants. So that's really weird. You know, we've been told this whole time, and you have been told since your first days in science as a middle schooler, that mass is neither created nor destroyed, right? Conservation of mass. Well, it's not exactly true. Mass energy is neither created nor destroyed. Mass can be converted to energy, energy can be converted to mass. And so this is the famous equation from Einstein's relativity work. So let's calculate this energy. So we have this reaction. So we have heavy hydrogen, so 2 deuterium atoms. You know it's hydrogen, even though it says D, but it's hydrogen because it has this 1 proton there. So 1 proton. So that's the atomic number. This is review for you guys from freshman chemistry, but that's a while ago. So, and then this up on here, up on top is the mass number. Which is equal to protons plus neutrons. So proton plus neutron is 2, so that means there's 1 proton and 1 neutron. The difference between those numbers is the number of neutrons. So if you get those 2 hydrogen or deuterium atoms to touch, which is hard because they're both positively charged. So it's really hard to overcome that Coulombic repulsion. But if you get those nuclei to touch, boom, they release an enormous amount of energy because they make a helium nucleus. So they become a helium. So we're changing the identity of the element. The 2 nuclei fused. Look here now, both those protons are now in the same nucleus. So we have a helium atom. And the 2 neutrons are still in there, so we have 4. It's a mass number of 4. And then the energy is released in terms of gamma rays and velocity and so on. So that's a gamma ray. It has no protons, no neutrons. It's light, essentially. So let's look at the mass difference, the products minus reactants. And so here we need to go to the isotopic tables and look up the specific masses of the isotopes. So we go to find the helium-4 mass right here. And it's 4, okay, but you got to be precise, 4.002602. And 2 of the deuteriums, here's the 2, this 2 is right there. And then the mass of the deuterium is right there. So do you see where the The 2 came from in front. That's the both deuteriums, and that's the mass of a single deuterium, 2.013553. And when we take this difference, we see that it's not 0. If we had perfect conservation of mass, it would be 0. We had masses as reactants, we have masses as products. They called it a mass defect. They detected this, and they didn't understand where this missing mass was going. So they called it a mass defect. Then when Einstein came along, then we realized, oh, that missing mass was turned into energy. So this is the missing mass. Let's take this mass and put it into Einstein's equation. So this is the missing mass here times the speed of light squared. And so you've got kilograms, meters squared per second squared, that's a joule. And so it's 2.21 times 10 to the 12th joules per mole. Okay, we're so used to using scientific notation that doesn't mean a lot to us. Okay, we see 10 to the 12 joules and it's just 10 to the 12 joules. But you got to get your mind around what that means. So this is, if you're talking about per mole, it's 4.03 grams per mole of deuterium. And so that's 548 gigajoules per gram of deuterium. Gigajoules per gram, okay? This is what we get from oil. 45 gigajoules per ton of oil. That's unbelievable. So 2,000 pounds of oil gives us 45 gigajoules. 1 gram of deuterium gives us 10 times more. Yeah, that's unbelievable amount of energy. Yeah. That's why a bomb that's smaller than this cabinet here can take out a city. If it's a thermonuclear bomb, if it's a fusion bomb, one that fuses deuterium. It's that much energy. That's also why a small amount of that could power all of our homes for a year.
Why don't we do that?
We don't know how to make fusion in a controlled manner.
Are we trying?
Yeah, yeah, it's awesome. Yeah, so that's what we're trying right here. This is where some, not a lot, but some of our tax dollars are going. This is the Sandia machine. It's a Sandia National Laboratory, and they're trying to work their way up to fusion. Now, look at what this scientist has. She's got these little fine gold wires. Now, you guys had to have physics too, or electricity and magnetism, right? And when you run current through a wire, okay, so if you run current through the wire this way, so I'm going to say I this way, that's the thumb, okay, and the current charge going one direction creates a magnetic field. As it ramps up, it creates a magnetic field. That's the right-hand rule. It's going to go around that wire in a clockwise manner. Okay, so it's going to create a magnetic field like this. B, or let's call it Z because that's what they call it. Okay. Okay. Z, and then this one we run the current the opposite direction. I. And it creates a magnetic field going the opposite direction. So that thumb's going down, and you see this is going like this, right? And this one's going up, and it's going like this. And so now we have north and south magnets. And the north and south magnets, what are they going to do? They're going to be attracted to each other. Okay. So they've determined that these gold wires, what happens when you try to send like I don't know, 1,000 or maybe even 1,000,000 amps through a tiny gold wire? Okay, it evaporates. I mean, it just evaporates the gold wire. But the magnetic force is imparted to the gold atoms right before it evaporates. Isn't that cool? So this current, like if I'm that wire, the current like shoots through my wire, and immediately I'm attracted to the other gold wires. But I now have no bonds left, and so all my atoms move in the direction of the force. So they shoot this current in opposite directions on these wires, and they all move towards the center because there's like an array of magnetic fields. So you have north-south, south-north, north-south, south-north, and all of these gold atoms come crashing into the middle. And you can put a target in the middle. And so part of getting fusion to occur is to get those nuclei close to each other. So if you have a salt like a lithium deuteride, so in this middle target here, if you put a little stick of lithium deuteride, these atoms, that's a salt now. We're not dealing with a gas. We don't have to worry about deuterium gas. We can have lithium holding on to deuterium in a solid form. And then you have all of these gold atoms, which are really heavy, slamming into that stick. We're going to compress that stick, aren't we? Can we compress it enough to get it to fuse? We can if we get to a high enough temperature. So the velocity of those gold atoms can tell us the temperature, and the impact on that fusion target, it can also tell us the temperature. So if we can get high enough, we can pinch that fusion target and create fusion. Okay. So this is the amount of power they're talking about, 290 trillion watts. That's how much electricity they're throwing through those gold wires in order to impart this. And this is what it looks like. That's the electricity that's not used. That's the waste electricity on top of the cooling pool. So they blast this thing for 100 nanoseconds. And so it's not a lot of over a long period of time, it's not a lot of joules. It's about the amount of joules that you have for 200 watts, two 100-watt light bulbs. Okay, but if you put that many joules into those gold wires in 100 nanoseconds, remember watts is joules over seconds. So a narrow, tiny time drives up your power. So they dump all of these little space age looking things, like right here, this thing right here, that's a capacitor. It's an ultra capacitor. So all of these are capacitors that are flowing current into those gold wires. And the charge that builds up on the apparatus goes through this cooling pool, the water, and is going to ground. You see, this is a ladder right here. So that gives you a sense of scale. That's 3 rungs on a ladder. So that's how big a person would be. And this is just the static or waste electricity that's going to ground. So most of the electricity went through the gold target, but the waste electricity went to ground, and then they can set up another experiment. So it's a pretty amazing thing. They got to 1.6 million degrees. They're aiming for 3 million degrees or higher. So they're pretty close. So this is called a Z-pinch. They call it the Z machine. They're using the magnetic field to squeeze that target. This is inertial confinement with a laser, or laser confinement, the National Ignition Facility. So these are 2 national labs that are in competition with each other. And that's always the best way to innovate, right? You put 2 teams in competition, they are going to be focused on winning the prize, right? And so this one, did we watch the video of the beamline in the fall when we talked about lasers? Do you recall? I'll play it just so you can see what we're talking about. Let me shrink this down. If I can get it to show up. Okay. Come on, computer. There we go. Okay, you can see that. All right. I don't have any sound. It's not cooperating. Uh-oh. Well, we've only got 3 minutes left, but I will send out that link on Blackboard so that you guys can watch it. It's an amazing video talking about how we're compressing that deuterium tablet with the lasers. So they actually got to the point of positive energy balance. And so there's a whole video talking about ignition, where they've ignited fusion in this particular experiment. Now, they calculate the amount of light going into the target, the energy of the lasers going into the target, and they got more energy out than in. But they don't have positive energy balance for the whole facility yet. Okay, so the whole facility is still using more power than they're getting out. But at the target, they flipped it over. They're getting fusion energy out. So they're hitting it with lasers. They're creating the fusion reaction, and they're measuring the X-rays and the gamma rays and everything that's coming out from that fusion reaction. So we're actually controlling fusion. We can make fusion happen with a nuclear weapon. We can't control it. So we know how fusion works. We know what the signals are that come out of a fusion experiment. You know, we have done downhole tests of fusion devices, but we haven't been able to control it. It destroys the equipment and all of that stuff. So how do you harvest the heat from a fusion reaction in a stable manner? Right, that's the question. But this would solve all of our energy problems. Deuterium is abundant in the ocean. There's no carbon associated with it. There's obviously going to be carbon used in the process, but in terms of the amount of energy we get out of it, you saw 1 gram of deuterium can replace 10 tons of oil. That's pretty good. 1 gram versus 10 tons. Yeah. So this is when people say with current technology, you know, they always try to scare you. With current technology, we're going to die in 2 years. You know, that phrase with current technology there's a lot that's carrying a lot of weight. And when are we ever going to stay at current technology? We don't do that. We don't stay at current technology. So don't suffer from the climate anxiety that your generation is suffering right now. A lot of people are worked up over this. We're not going to stay at current technology. We never have. We never will. You can't restrain the human ingenuity. So with that, be excited.